In this section, we'll focus on masked language modeling, one of the core training ideas behind modern NLP systems. We'll cover how it works, why it matters for language understanding, and the kinds of interview questions engineers are expected to answer. The goal is practical interview prep, from understanding the mechanics clearly to turning that knowledge into strong portfolio projects for LLM and AI engineering roles. Here's the agenda for this section. First, we'll define masked language modeling, or MLM, and look at how it works, including its role in BERT. Then we'll cover why MLM matters, especially for learning bidirectional context through self-supervision and transfer learning. After that, we'll talk about the trade-offs, particularly where MLM-based models differ from decoder-only approaches. Finally, we'll connect this to interviews and portfolio projects you can use to show these skills. Masked language modeling, or MLM, is a self-supervised way to pre-train a language model. The idea is simple. We hide a few tokens in a sentence and ask the model to predict the missing originals. To do that well, it uses both the words before and after each mask. So instead of just guessing the next word, the model learns richer context from the full sentence. Here's the key difference between masked language modeling and causal language modeling. In MLM, the model can read the entire sequence before predicting a missing token, so it uses both left and right context. In causal language modeling, it can only look at the words to the left, predicting one token at a time. That makes MLM stronger for language understanding, while causal models are the standard choice for text generation. Here's how the masking works in BERT. During pre-training, the model picks 15% of tokens to predict. Of those selected tokens, 80% are replaced with the special mask token, 10% are swapped with a random token, and 10% are left unchanged. This mix is important because it stops BERT from relying only on mask tokens, which never appear later at inference time. Here's how the masking pipeline works. We start with raw text and randomly choose some tokens to corrupt. Then we apply the 80/10 tokens, woo. Most selected tokens are replaced with a mask token. Some are swapped with random tokens, and some are left unchanged. The model's job is to predict the original tokens. That reconstruction objective helps the encoder learn rich context, including syntax, meaning, and long-range relationships, from unlabeled text alone. Masked language modeling scales well because it doesn't rely on hand-labeled data. The supervision is built into the text itself, so almost any large corpus can be used. That includes web pages, books, code, and even medical text. As a result, we can pre-train on massive amounts of data, then reuse those learned representations by fine-tuning one model for many different downstream tasks. This slide shows the transfer learning story behind BERT. First, you pre-train on a huge unlabeled text corpus using masked language modeling, so the model learns general language patterns cheaply. Then you fine-tune it on a much smaller labeled dataset for a specific task. Finally, you deploy it for things like classification, question answering, retrieval, or extraction. That pre-train then fine-tuned pipeline is the core reason BERT made production NLP so practical. The key insight here is that MLM pre-trained encoders are built for understanding text, not generating it. That makes them especially strong for business problems like search and retrieval, where semantic similarity and dense embeddings matter, as well as classification tasks such as sentiment, intent, compliance, and moderation. They're also very effective for reranking in RAG pipelines, and for extraction tasks like named entity recognition and span detection. A strong project pattern is domain adaptive pre-training. You start with a general masked language model checkpoint, then continue pre-training it on text from your target domain. After that, you fine-tune on the labeled downstream task and compare the results to a baseline. What makes this valuable is that it shows the full workflow: careful data curation, solid pre-training intuition, and a measurable improvement story that hiring managers immediately recognize. Here's the core Hugging Face toolchain I used. AutoModelForMaskedLM lets you load any masked language model checkpoint in a single line. DataCollatorForLanguageModeling handles dynamic masking during training, with a default masking rate of 15% per batch. For training and evaluation, one key detail is that dynamic masking can make metrics fluctuate, so freezing the masks gives more stable results. And finally, the Hugging Face Hub makes it easy to publish trained models as clear, inspectable portfolio artifacts. These implementation details are what separate resume-level familiarity from real engineering competence. You need to get tokenization right, including special tokens and chunk-long documents into valid context windows. Whole word masking usually gives a cleaner training signal than masking subword pieces. Dynamic masking changes each epoch, while static masking is reproducible. And for reliable evaluation, freeze masks. Then there's infrastructure, effective batch size, gradient accumulation, and mixed precision all matter. Masked language modeling has a few important limitations. First, only about 15% of tokens are selected for prediction, so most positions provide no learning signal in each step. ELECTRA highlighted how sample inefficient that can be. Second, there's a train inference mismatch. Because the special mask token appears during training, but not at test time, though the 80-10-10 masking strategy helps a bit. And finally, MLM-based bidirectional encoders aren't naturally suited for text generation. So why did modern LLMs become decoder-only? The careful answer is that masked language modeling was excellent for bidirectional understanding, and it still powers many strong encoder systems. But at large scale, generative training unlocked the behaviors that mattered most at the frontier: reasoning, instruction following, and few-shot learning. That's why decoder-only models took over. At the same time, encoders still lead in production for embeddings, reranking, classification, and moderation. Here are 3 strong masked language modeling projects for a portfolio. First, domain adaptive pre-training. Continue training on a specialized corpus and measure gains on classification or retrieval against a baseline. Second, fill mask error analysis. Inspect predictions for domain-specific terms and show how the vocabulary shifts after adaptation. Third, compare subword and whole word masking. Then quantify how each strategy affects downstream task performance. Masked language modeling signals several skills employers value. First, it shows you understand self-supervised learning, including pre-training objectives and how representations transfer to downstream tasks. It also demonstrates fluency with the Hugging Face stack, from tokenizers and data collators to trainer workflows and hub deployment. Just as importantly, it reflects disciplined experimentation and good model judgment, especially knowing when an encoder is a better business fit than a generator. Here are the common interview questions I'd expect on masked language modeling. Be ready to explain that MLM learns from bidirectional context by predicting masked tokens in a self-supervised way. Know why BERT uses the 80-10-10 corruption split and how MLM differs from causal language modeling. You should also be able to say when encoders are the right choice, their main limitations, and how to adapt them to a new domain through continued pre-training, fine-tuning, and careful evaluation. This is where masked language models still really shine in practice. In many production NLP systems, the core need isn't open-ended text generation. It's strong embeddings, reranking, classification, and information extraction. That's why MLM-based encoders are still a backbone of real-world pipelines. And if you frame your MLM project around a specific business domain, it becomes much more concrete and much more compelling to hiring managers. Here's the career strategy in one line. Don't learn machine learning theory in isolation. Start with the basics. Then, build one practical project where a model improves a real downstream outcome. Measure the baseline, show the gains, and document the full process clearly. Most importantly, Connect that work to an actual business use case or hiring need. That's what turns study into a portfolio story that gets attention. Here are the key takeaways. First, know the mechanics. Masked language modeling typically masks 15% of tokens with the 80 divided to 10 TWIR, uses bidirectional context, and trains on reconstruction. Second, know the trade-offs. It's sample inefficient, has a train test mismatch from masking, and isn't built for generation. And that's fine. Most importantly, build something practical. Show a measurable gain from domain adaptive pre-training. Publish it, and tie it to real business value like search, compliance, extraction, or retrieval.